Welcome to my talk. My name is Max, and I will be presenting our work called String Indexing for Top K Close Consecutive Occurrences. This is a joint work with my two supervisors and another associate professor and a PhD student, all from the Technical University of Denmark. So to begin, I'll first explain what exactly is the problem we're trying to solve here. And to do this, I'll first discuss the classic string indexing problem, and then we'll see how we differ. In the classic string indexing problem, we are given a string S, and we want to pre-process it into a data structure such that we can answer queries of a pattern P and find all the occurrences of P in S. Here is an example. And given our pattern P, we want to find all the places that P occurs in S, and specifically we want the starting positions of those occurrences. So in this case it would be 0, 6, 11 and 13. In this work we study a variant of this problem. We still want to pre-process S, but now our query consists of both a pattern P and an integer K, and the goal is now to find the K closest consecutive occurrences of P in S. Here a consecutive occurrence is a pair of occurrences of P, such that no other occurrence of P is found in between, and we want the K closest ones where we measure the distance in the distance between the starting positions. For example, an example query here could be an, and our k is equal to 2, so we want the two closest consecutive occurrences of P and S, which in this case would be the pair 11 and 13, and then the pair 6 and 11. As far as we can tell, this problem hasn't been studied before. However, in 2015, Navarro and Tanketian studied a closely related problem where the goal was to find consecutive occurrences where the distance fell within some specified interval. Another line of work is finding all pairs within some distance constraints. The difference here is that they spend time proportional to all the pairs instead of only the consecutive ones. And finally, there's also a lot of work in top K queries for the document framework. Here there is not a single index string S, but a collection of them called documents. One problem in this framework is finding the K document with the closest pairs. A crucial difference here, however, is that within a single document, only a single pair is considered, instead of up to K pairs in a single document. So, what are our results? Well, we provide two trade-offs. Firstly, we provide a trade-off with optimal query time, that is O of m plus k. Here m is the length of the pattern, and it uses O of n log n space. We also provide a linear space trade-off that instead uses O of m plus k to the 1 plus epsilon, where epsilon is any constant between 0 and 1. To help us talk about this problem, we'll first introduce the suffix tree. This is a very well-known standard string indexing data structure that is the compressed trie over all the suffixes of S. And this structure allows us to easily perform pattern matching, because we can simply from the root trace down our pattern P, and then we end up at a node which we call the locus, and then all the leaves below the locus is going to be all the occurrences of P. This allows us to discuss some basic trade-offs for this problem. Firstly, say we don't want to use any more space than just a suffix tree which takes linear space. Well, then we can simply trace down a pattern P as we've just done, and then gather all the occurrences of P, and from those construct all the consecutive pairs, and then output the K smallest. And using a linear time selection data structure, we're able to do this in m plus occurrences time. And here occurrences is the number of occurrences of P in total, and note that this can be much larger than our K which we are given at the query. On the other end, say we want to use more space but want optimal time, then we can simply at every node in the suffix tree store all the consecutive occurrences below in sorted order. And then once we found our locus, we simply output the K smallest of those from the list stored at the node in the suffix tree. And this gives us an optimal time of m plus k, but it could take reductive space. So our goal is now that we want to pre-process S to find the K closest consecutive occurrences of P, and we want to use small space, hopefully linear, And we want a query time that's dependent on the length of the pattern, which we denote m, and our k only, not the number of occurrences of p. So this is the outline of what we're going to go through. We're going to start with our first trade-off, which takes n log n space and gives us optimal query time. And then we're going to gradually improve this until we end up at our linear space trade-off that uses O of m plus k to the 1 plus epsilon query time. The foundation for our first trade-off is the heavy path decomposition, which is a decomposition for trees in general, and we're going to use it on the suffix tree. The heavy path decomposition is constructed by starting at the root and then picking the heaviest child, that is the child with the most descendants, and keep doing this until you reach the leaf, and this path now becomes your first heavy path. And all the edges branching off that heavy path become light edges, and then all the remaining subtrees are recursively decomposed, and you keep doing this. This is how it looks for a suffix tree example from before. And as I said, we end up with a set of heavy edges and a set of light edges. And the important property that we're going to use here is that any root to leaf path in the suffix tree now is going to intersect at most O of log n heavy paths. So say I now have some heavy path in the suffix tree, which is what is depicted here. It starts somewhere in the suffix tree, and then the heavy path continues all the way down to a leaf. And we're now going to observe the set of consecutive pairs on this path. And we're going to starting at the apex of the heavy path here. We see in this case we have 5 pairs of varying length. We have a pair of distance 1, a pair of distance 6, 4, 3, 5. And now we're going to look and see what happens once we traverse down in the path. So going from the apex to its child. Well, 2 leaves are going to drop off, a 1 and a 19. And what does this do to a set of pairs? Well, we see that for the 1, a 0-1 pair is going to disappear, and a 1-7 pair is going to disappear, and a new pair is suddenly created, the 0-7 pair. And when 19 drops off, well, the pair that it was a part of simply disappears, the 14-19 pair. And when we move further down in the path, 2 more leaves drop off, now 0 and 11. And when the 11 drops off, 2 pairs disappear and a new pair is created. And when the 0 drops off, the pair it was a part of simply disappears. And this process continues all the way down till you reach a leaf, at which point no pairs are left. The important property to observe here is that once a specific consecutive pair disappears, it never reappears again. So there is some interval on this heavy path where the specific pair exists, and outside that interval it doesn't exist anymore and it will never reappear. So we're going to exploit this and encode these intervals as lines. So for every pair in our set here becomes a line where the x-coordinate of the line is going to be the distance of the pair. So for example, see here we have a pair of distance 1. That becomes this line, and we have a pair of distance 3, this becomes this line. And the 2 y-coordinates of the line is going to be the interval on the depth of the heavy path for which that pair exists. For example, the pair of distance 1 only exists on the very apex of the path, and the pair of distance 3, well, that exists at the apex and it survives down to the next node, after which it disappears. And say I now come with a pattern P, and that pattern happens to land on this heavy path. Well, now to find my k closest consecutive pairs, it's simply a matter of tracing a line at the depth of the locus of the pattern on the heavy path to the right, and then return the k first lines segments that this line intersects. And that is going to correspond exactly to the k pairs of smallest distance that exists at this depth. And this problem turns out is a well-studied problem called the orthogonal line segment intersection problem. And there exists a linear space data structure for this, linear in the number of line segments in the data structure, that can give us the these k first lines in linear time, O of k time. So this becomes our data structure. We construct the heavy path decomposition for our suffix tree, and then for each heavy path we build the line segment data structure. And this ends up taking O of n log n space. The insight here is that each leaf in the suffix tree can contribute a constant number of line segments in each line segment data structure it appears in, which corresponds to every heavy path that it intersects on the path from the root to that leaf. So that's going to be O of log n for each leaf, and there's n leaves, so in total O of n log n space. And our curve is just as we described. It's going to take us O of m time to trace down our p and find our locus. And then we're simply going to query the line segment data structure, which takes O of k time. So in total, we get optimal query time of O of m plus k. So that was our first solution done. As we mentioned, this has the optimal query time of O of m plus k, but it uses more than linear space. So now we want to see if we can improve this space usage. And we're going to do this by starting with relaxing the problem. So assume that we know k at construction time. That is, we're now in a new problem. Now we want to pre-process s and k to get a data structure such that when I come with a query that only has a pattern, we're going to return the k closest consecutive occurrences of p. To solve this problem, we're going to decompose the suffix tree again, but this time using another tree decomposition. We're going to use the cluster partitioning scheme, and we're going to group the nodes of the suffix tree. The suffix tree is what you see here as a triangle. We're going to group the nodes into clusters where each cluster has at most k nodes. And they're going to be grouped in such a way, or clustered in such a way, that the clusters only overlap each other in exactly one node, which we call the boundary node. And there's going to be two types of clusters. There's the leaf cluster, which has only one boundary node, and then all the trees hanging off that boundary node have a total size of at most k. And the other type is what we call the path cluster, which has two boundary nodes. And the path between the two boundary nodes we call the spine. And everything that hangs off the spine is going to be small subtrees of a total size also at most k. And we're able to do this and get at most O of n over k clusters. And that is the cluster partitioning, and now we're going to move on to the data structure. For every spine in a path cluster, we're going to build our line segment data structure from before. But with the caveat that we're only going to store the k closest line segments at any depth. And we show in the paper that it turns out that any one of these line segment data structures is now going to have at most O of k line segments over the entire spine. So the total size of this data structure with O of n over k clusters, and each of them has size O of k, is going to give us linear space. And with this, we are able to answer queries to our problem. So say we get a query p, and we trace it down in the suffix tree, and we land on a spine in a path cluster. Well, then we simply query the line segment data structure for that spine, and that's going to give us our answer in O of m plus k time. Another case is that we land up in a small subtree hanging off a spine. Well, now, because we're in such a small subtree, there can't be that many occurrences of p. So even if we take all the occurrences of p and construct all the consecutive occurrences and only report the O of k, well, it's not going to take us any more than O of k time to report them at that point. And the final case is that we land in a leaf cluster, and the same thing is true here. There can't be that many occurrences of p, so we get a query time of O of m plus k. So that is our second solution done, which has linear space and optimal query time, but however for the relaxed problem where k is known as construction time. Now we're going to move back to our original problem, and we're going to use this solution to solve it. So we're back at our original problem where we want to pre-process S, and now K is given a Curie time. So we're going to take our solution from before and we're going to apply it recursively. This here is the suffix tree as we know before, and now we're going to cluster it, but with a cluster size of square root n. And for every spine, we're going to build the line segment data structure just as we did before, and storing only the square root n closest line segments at any depth. And now all the small subtrees that hang off the spine, we're going to recursively decomposition again, but with cluster size the fourth root of n. Again, building the line segment data structure for every spine, and again, taking all the subtrees that hang off and recursively decompositioning them again. And we're going to keep doing this until we reach a constant cluster size. We can keep doing this for O of log n times until we reach a constant cluster size. And every level of every level of the recursion takes no more than linear space, since it's a disjoint decomposition of the suffix tree. So in total, it's going to use O of n log n space. With this, we're able to answer queries. So say I come with a pattern and a K, and I trace down P in my suffix tree and I land on some spine. And note here that I'm always going to land on the spine of some cluster, or in a constant size cluster, in which case the problem is solved. So I land on this spine, and there's now going to be two cases. Either K is smaller than the current cluster size, or said in another way, there's going to be enough line segments stored for this line segment data structure that I can answer my query, in which case I simply do in O of K time. The other case is that there is not enough answers stored. Now notice that we're actually hanging off a subtree in a cluster of size at most the fourth root of n squared. So there's not going to be any more than square root n occurrences of P, and this is going to be less than K squared. So we can simply construct all the occurrences of P, construct all the consecutive pairs, and output the K smallest, and it's going to take us O of n plus K squared time. And thus we can always answer queries in this time. And that is really the main solution of our paper here. In the paper, we further improve this solution. I'm going to skip over the details here, and I'm going to refer you to the paper for those. We optimize it in two steps. Firstly, we optimize the space. In every cluster, we essentially reduce the universe size within the cluster and then apply some clever encoding. And this can get us to linear space in the word RAM model. So we're going to use O of n words. And finally, we tune our cluster size. So instead of getting this O of n plus K squared, we're going to get a O of n plus K to the 1 plus epsilon for an epsilon, for any constant epsilon chosen between 0 and 1. That is the end of my presentation. Thank you for listening. As I've said, details are in the paper, and if you have any further questions, I will be available to answer them in the question session.